Okay, now moving on to the next section here of alcohols, we have dehydration. The dehydration of alcohols requires concentrated sulfuric acid. It produces an alkene, right? Low concentrations of water needed to favor that alkene. Remember, we go through a carbocation intermediate. We favor the Zaitsev product. And if we do bimolecular dehydration, we get an ether. So we'll see down below how we can favor that. All right, so looking at this first little section here, let's go back and take a look at the overall reaction. So remember, the first step that we have here is sulfuric acid, low concentration of water. Often would see brackets around it like this. So if you recall, we're grabbing an H, right? That H plus is coming from H2SO4, so we get HSO4 minus as a combo there. I'm just going to write it out this way because I've run out of space. But we're grabbing an H from H2SO4. Okay, that'll form this intermediate, right? And then what happens next is that's going to leave. And here's where we're left with a carbocation, right? And that, again, to point out, is your RDS. It's your rate determining step, right? So if you look down below, it's this step. That is your RDS. So the more stable the carbocation, the more likely it is to form and have a lower activation energy for that step. And then the last step here is you have HSO4 minus, and it's grabbing one of the H's off of this end here. So we're coming around and we're doing this to give you your final product there, your alkene. Remember that rearrangements are common, right, since we end up forming that carbocation. Now at a lower temp, so 140 and below, right, so notice there it says higher temp, and let's highlight that a little bit more here too. So at a higher temp here, higher temp for us means about 180 degrees Celsius or above. In that case, we end up seeing the alkene. We favor the alkene. Now, so that's case number one. Let's make a little note here. Okay, if we look down here below, our case number two, that's a lower temp. So 140 and below is what we're going to use to designate that as being a lower temperature reaction. So at a lower temperature, let's take a look at something like methanol. Why don't we take a CH3OH. So there's methanol. And here we're going to use still conc H2SO4, except now we're going to have a lower T, or something like 140 degrees Celsius there. Now that first step is still protonation, so we're still going to grab an H from H2SO4, right? So we're going to kind of write it out like this to cheat a little bit. Now here's what that's going to give us, and I don't know if you thought about this on the last problem, but it's interesting. So look, we have this little guy, right? We have the good leaving group. Okay. Now, in the last step of, well, the second to the last step of the last reaction, we formed a carbocation. That's not going to happen here because primary carbocations are not going to be stable. But we have this whole ocean of ethanol. Remember, it's not like there's one molecule. You're in the Atlantic Ocean of this stuff. It's everywhere. So what can happen at a lower temperature is we can come around here and we can do this. Right, so what can happen at that lower temperature is we can come around and we can do this. Right, and when we do that, look what we get. We get CH3O, HCH3, and plus charge. Now, last step of this reaction here is like your cleanup phase. So you could use HSO4 minus as a base. You could use methanol also as a base. So either one of those are acceptable to use. And then we'll grab that H and we'll come down, and that's going to give us CH3, OCH3. And again, to point out something interesting, this is an ether. So again, another reaction that we're going to see when we get to chapter 14. So that's why when we get to that chapter, I mentioned this before, we've covered almost everything in there. Almost all the reaction we'll have seen by then. And so it's best for symmetrical ethers. So it's difficult, like in the second step, you can't add like ethanol there because it takes place too quickly. And it's also better for primary because then you have less chance of forming carbocations. The last couple of reactions here are straightforward. They're really just observed reactions. So they're the formation of alkoxides. So sodium, if you think about its reactivity, it's up here, and then below it is potassium. So potassium is more reactive than sodium because it's lower on the periodic table. So you use something like potassium down here below when you have an alcohol that has a higher pKa. Remember, tertiary alcohols, primary, secondary, tertiary, 16, 17, 18. Right, that was our trend. Here for pKa's. Here's a primary, about 15.5, 16, close enough. Here you have solid sodium. And what you form here is ethoxide and T-butoxide. It'd be potassium tert-butoxide. So this is something that can be used in ether synthesis also. So you can form an RO minus, and then you can react that with another alkyl group to form an ether. So just kind of looking down here below, I ran out of space, so let's write it up here. So what if we had CH3, CH2OH? So if we took that and we added sodium to it, you would get CH3, CH2O minus, right? So you can carry that out just like in a separate little reaction. You wait till it's all complete, and then you would go through and you could add in some type of good SN2 substrate. How about like CH3I? So then we'd come around and we would do that. So that would give us CH3, CH2O, CH3. So this is an unsymmetrical ether, and it's called Williamson ether synthesis. Now the last reaction in this chapter, it's an interesting reaction. Sometimes we go over the mechanism for this. This semester we're not going to. It's not something that you're going to miss out on because there's a whole chapter in second semester that deals with carboxylic acids and their derivatives. So we're going to see this reaction and the full mechanism again, so we're not going to miss out on it. But I wanted to point out to you that it's a reaction that involves the use of an alcohol being mixed with a carboxylic acid, and we use an acid catalyst here. So let's put brackets around here. This is also important. So often concentrated H2 SO4 is required here, and you make an ester, and you have water as one of your products there too. Esters smell very good, and generally carboxylic acids have a bad smell. So looking forward to it. In lab next semester, we'll make isopentyl acetate, which is banana oil. We make it using acetic acid, which has the smell of vinegar, right? And isoamyl alcohol. So you add these two things together and you make isoamyl acetate, which is banana oil.